Going to speak about something which is a little bit off the mainstream of this conference, I believe. So I decided to give a board talk, and hopefully it will be easier to follow. But also, because of some time constraints, it's a very broad subject. I would be probably forced to say some things, maybe not very precisely. And so the goal is to somehow give a flavor of the subject. So basically, this is about the spectral theory of measure-preserving systems. So suppose we have a measure-preserving system. We always assume that the measure is finite, can assume that the probability measure, T, is a measure-preserving transformation. And so that we are in the setting of ergodic theory. So then the spectral theory begins by considering what is called the Koopman operator, U on L2 space, the Hilbert space. So this is the operator U equal to UT, which takes F to a composition of F with T. So in general, by measure-preserving property, this is an isometry, and if T is invertible almost everywhere, so if T is invertible almost everywhere, then U is a unitary operator, and then we are in the setting when we can apply spectral theory for operators in the Hilbert space. Now, okay. Now, what are the things that are studied in spectral theory? Certainly, eigenfunctions, eigenvalues, right? So we recall that function f is an eigenfunction. If such equation is satisfied, f should be not a zero function in L2, and because it's unitary, so we always have eigenvalues of f equal to 1, and then there are always invariant functions, right? So it's clear that every constant function is invariant, and therefore it is natural to look at the orthogonal complement of restrict our operator to the space L to 0, which is the set of functions f in L2, which are orthogonal to constant 1 function, or equivalently functions of mean 0. So the interesting dynamics happens there. Okay, so therefore, I mean, there's the trivial eigenvalue equal to 1. Now, many, okay, so I should define what is a spectral measure. So the given a test function, sometimes called a test function, in L2, the spectral measure sigma f on the unit circle is defined by its Fourier coefficients. And well, the normalization I like is basically looking at T as R mod B. So I want to define the following way, that the Fourier coefficient of the spectral measure at the point minus n, which is right at integral from 0 to 1 e to the 2 pi I omega n, integrate with respect to this measure. So this should be by the scalar product in the product of U and F with the function itself. So this is well known that this is a positive definite sequence, so it defines uniquely a Borel probability measure on the unit circle. And so it's a positive measure, or because has total mass equal to square of the norm. And so we will be interested in some dimension properties of this. Now, it is well known that many ergodic properties can be actually spectral properties. In other words, they depend only on this Koopman operator. It can be expressed in spectral terms. In particular, so let me just mention three most well known. So U is ergodic, if and only if, well, there are no invariant function, no non-constant invariant functions could be stated as saying that one is a simple eigenvalue. Then there is an important property of being, T is right. The whole system is ergodic. The system is weakly mixing. So I don't give the original definition. There are many equivalent definitions. The spectral characterization is that it's weakly mixing if and only if there are no other eigenvalues rather than the trivial one. So basically, if and only if ut has no discrete spectrum on the function source of mean zero. And mixing property, so the system is mixing, can be also stated in spectral terms. This is if and only if for every f, the spectral measure is a Reichmann measure. The Reichmann measure, which means that the Fourier coefficients tend to zero. Zero as k goes to infinity. Okay. So now the question is, so we are going to be interested in dimension of, basically in the local dimension of the spectral measure. The question is, what good can this give? What, why is it good? That was the first introduction. So dimension of spectral measures. What is it good for? So I'm going to consider actually the local dimension. So I denote the local dimension of any measure. Let me say just any measure mu or mu at the point omega, defined in the usual way. This is a fixed notation. So one reason why dimension of spectral measures may be interesting, this is related to the question of quantitative Wick mixing. Quantitative Wick mixing, which I want to abbreviate QWM. So if we think about Wick mixing means that there is no point mass, right? So there are no point masses. So quantitative Wick mixing maybe make this quantitative, so that the balls, that there are some bounds on the measure of the ball as the radius goes to zero. So some kind of estimate like that the spectral measure of the ball is bounded by constant r to the alpha. For alpha positive, r sufficiently small. That is good. Okay, if we cannot do, it cannot get such power estimates, maybe some weaker function, but at least some function which goes to zero at zero. And here one should point out that this cannot be true in general for all functions. So this is usually for f, so-called nice, sufficiently nice test function. If it's a smooth system, it could be smooth functions. And in the symbolic case, so we'll see that functions which depend only on finitely many symbols. Now, another way that, and of course, where can such estimate be obtained? Such estimate is basically very close to saying that there is a lower bound for the local dimension of the spectral measure. And ideally, we would like to have such estimates uniformly. So just at arbitrary. So if such estimates are uniform in omega, then we can make some strong conclusions from that. There are other formulations of quantitative weak mixing using the other definitions, but I don't want to go into that for lack of time. So another reason why this could be interesting is to show singularity of the spectrum. Singularity of the spectrum. So in general, spectral theory of measure preserving system has the aim of deciding what kind of spectral type is. It could be pure discrete, or it could be Lebesgue, or singular continuous. So one of the questions is, can we decide that the spectrum is singular? And of course, there is a very simple fact that if the local dimension, well, again, it's for any measure, if the local lower local dimension is greater than 1 for Lebesgue almost every omega, then the measure is singular with respect to Lebesgue. And this is, of course, immediate from the definition. So let me recall that. So this is should not be surprising because, okay, here we talk about Lebesgue almost every point. So recall that the Hausdorff dimension of the measure can be expressed using the local dimension as supremum of positive S, such that the local dimension is greater or equal to S, but here it is for mu almost every S. For mu almost every S. So here we're talking about mu almost every, almost every omega. Here and here we're talking about Lebesgue almost every. This is, of course, a crucial difference. Now, so a tool which really helps understanding the local properties of spectral measures is what is called twisted Birkhoff sums, twisted Birkhoff integral. So I only stated everything for the z actions, but also everything makes sense and will actually be considered also for r actions, for flows. And then instead of Fourier coefficients, we consider Fourier transform. But many things are somehow work similarly. Oh, so what are the twisted Birkhoff sums, and why are they relevant? So, where's the erase? Okay. Okay, so now we are thinking about twisted Birkhoff sum. So again, we are still in the completely general case of measure preserving system, and so given given a test function L, given a test function F, so we consider an X point in the space, we consider the twisted Birkhoff sum. So if omega is equal to 0, we just get the usual Birkhoff sum. Okay, so here we put this term, exponential term, e to the minus 2 pi I omega n. And it turns out that the growth properties, how this function grows with n, is related to the local behavior of the spectral measure at omega. So in order to make this precise, define the following quantity. It's L2 norm of this twisted Birkhoff sum squared. Okay, so this is so basically right. So this is just can be written as normalized by n. Okay, can be written as this way, and then so we have the same term. This is a scalar product in L2, and simple calculation, which is very standard, shows that this is nothing but convolution of the Thayer kernel with the spectral measure at omega. Okay, where the where k n minus 1, it's the Thayer kernel. I think I skipped this computation for lack of time, but this is a standard computation. You put here some in terms of another variable. So let's say this is in terms of n, this is in terms of L, and then you use just the definitions, write it out, and you get a formula for the Thayer kernel. So it's known that the Thayer kernels are very nice. They're approximate the delta function, approximate unity. So from this, one gets several nice consequences. So from this, one gets several corollaries. First of all, if we look at this function, okay, so it's clear what the function is. So I take the twisted Birkhoff sum at the point omega, and take the L2 norm with respect to for this, the point function f is fixed, and then x varies over the space. So we can look at this as an absolutely continuous measure on the circle, and then it converges big star to the sigma f, right? Because it's a convolution with a approximate unity. So also one can see that the measure of a single point omega is actually the limit of this function normalized by n, and this follows from basically Wiener's lemma. Wiener's lemma. On the other hand, Lebesgue almost everywhere, right? So again, looking at this convolution, one can see that the function itself converges to the Rodon-Nikodym derivative of the absolutely continuous part of the spectral measure, Lebesgue almost everywhere. So from this one can somehow surmise that at least heuristically, depending on the asymptotic growth of this twisted Birkhoff sums, we could say something about the local behavior. So heuristically, we can say that if if the twisted Birkhoff sum grows like n, so this corresponds to the fact that e to the 2 pi I omega is an eigenvalue. If it grows like root of n, then this could, well, not exactly, this could indicate that there is a Lebesgue spectrum, right? So because basically it follows from the definition, and it was actually pointed out in the physics literature, or suggested that some intermediate growth between half and 1 should correspond to singular continuous spectrum. This is not exactly true, but to give some motivation. Now, so if you want to get something quantitative, just weak star convergence is not enough. So we'd like to have something more precise. And here there is a simple lemma. So this is would be called the folklore, but I learned it from a paper of Berthoff in '97. So the lemma says that for any fixed omega and for any r, for any radius, say from 0 to 1/2, we actually have an inequality that upper bound for the spectral measure of a ball of radius r can be bounded by constant over n gn of f omega, where n is 1 over 2r. So there is a very precise inequality, which of course can be easily obtained just from the lower bound on the Feyer kernel. So we know that roughly in the neighborhood 1 over n, 1 over 2n, so the Feyer kernel is at least something like n. So from this you immediately get this bound. And so of course notice that here it is the gn, not itself the twisted Birkhoff sum, but it's kind of integrated quantity. But in many in applications, actually, it turns out that it's enough to if we manage to get uniform bounds on the twisted Birkhoff sum, then it actually does give you can make such a conclusion. Okay, so now I finally get to define the system that I wanted to talk about. So this was a completely general. So the systems I want to talk about are substitution systems. And many things actually work in a greater generality, like for interval exchange transformations and translation flows, but I want to keep to the simplest setting. So, so how it is defined, there is a finite alphabet. So A plus is the set of all finite and empty words. And the substitution is a mapping from A to the set of words, which can be extended to finite words and to infinite words by concatenation. So formally, this could be viewed as a free semigroup, as a morphism of a free semigroup generated by the symbols in A. So in order to understand this, let's look at some classical examples. So the first classical example is called 2-or-more substitution. 2-or-more, 0 goes to 0, 1, 1 goes to 1, 0. And basically the game you play is you continue substituting. 0 goes to 0, 1, then it goes to 0, 1, 1, 0, and so on. So in this case, it has many nice symmetries, and you get in the limit an infinite word, which is actually invariant under substitution. So this is an important object. Another well-known example is Fibonacci. Fibonacci substitution, 0 goes to 0, 1, 1 goes to 0. So here, when you keep substituting, you see that the length of the Fibonacci number, that's the reason called Fibonacci. And the third well-known example is called Rudin-Shapira. Well, not like they really define the substitution, but it's just named after them. It's a famous Rudin-Shapira sequence, and it is actually on the defined on 4 symbols. So convenient to call them 0, 1, 0 bar, 1 bar. And the substitution works as follows: 0 mapped to 0, 1. 1 is mapped to 0, 1 bar. 0 bar is mapped to 0 bar, 1 bar. And 1 bar is mapped to 0 bar, 1. So here, there are also many symmetries. You could see that there is kind of involution putting this bar, and it's invariant under this involution. So, so the substitution systems actually, I mean, this is just a definition of a substitution. How do you get the dynamical system out of this? One can consider the space. It's a symbolic dynamical system. The symbolic dynamical system, the space is defined as a set of all two-sided sequences in the symbol in A, such that every word that you see actually occurs in some substituted symbol. So if you keep substituting long enough, you will see everything. That defines sort of the language of the system, and it is easy to see that this is going to be closed shift invariant subset. So we get a topological. So T is just the left shift. Right? T is just the left shift, and this is a topological dynamical system. Now, so there is an important object called substitution matrix. The substitution matrix codes basically it's an incidence matrix which codes how many symbols of which kind you have in the substituted letters. So the IG symbol is the number of J's in zeta of I. Okay, so for instance, in the well, let's say in the example, let's say 0 goes to 0, 0, 1, 1 goes to 1, 0, or 1 goes to maybe 1, 1, 0, 1. So it is defined this way. You go along the columns. From 0, you get 2 zeros and single 1. From 1, you get single 0 and 3 1. So this is a substitution matrix. So notice that it completely ignores the ordering, only knows the number. And so there's important special case when this matrix is primitive. So if this is primitive, this is called the primitive substitution. If this is primitive, in other words, some power is strictly positive, has only strictly positive entries, this implies that the system is minimal and uniquely ergodic. So there is a unique invariant measure, and we can talk about the measure preserving measure preserving. Are there any questions on this? But basically, it follows from Perron-Frobenius theorem that there is the measure is given by the frequencies of words. So we can show that and these are systems that have been studied a lot. They are, in some sense, very simple because they always have entropy 0. The complexity grows only linearly, but actually there is a rather wide variety of the spectral properties. So I'm not going to list all the spectral properties, but let me just say that the 2-amorph is known to have it has mixed spectrum. discrete. There is discrete component plus singular continuous. The Fibonacci has pure discrete spectrum, and it is actually measurably isomorphic to the rotation by golden ratio on the unit circle. The golden ratio. And the Rudin-Shapiro is one of the few examples where it's known to have Lebesgue components. So it has a discrete component plus Lebesgue component of multiplicity 2. So in fact, this is one of the mysteries here is that very few examples with Lebesgue components are known. On the other hand, it's hard to rule it out. So one of the questions is how to prove that the spectrum is singular. Okay, so now let me just mention that there are many open questions. In particular, there is a so-called Pizot conjecture. Maybe I will not write it for to save some time. So, familiar with the Pizot numbers and Bernoulli convolutions here. Also, there are an open question whether if the substitution matrix is a Pizot matrix, meaning that the Perron-Frobenius eigenvalue is Pizot, all the other eigenvalues are strictly less than 1 in absolute value, whether it implies pure discrete spectrum. So the Fibonacci is a special case. It's known for 2 symbols, and it's known in many examples, but the general case is still open. And so the other open question, as I mentioned, is the Lebesgue component. Okay, so I see that there's not much time, but I started a little bit late. How much time do I have? Okay, so let me at least define this sort of new tool that a relatively new tool that I want to talk about. This is called the spectral cocycle. Which was defined by joint work with Bufetov. So it is actually somewhat related to the okay. So suppose we have this substitution, and for any word, if you are given any word, define the word z of w, just the monomial. So we have three variables corresponding to each of the letters. And we define first a D by D matrix, whose entries are polynomials in Z. So first I write it formally, and then I give an example. Hopefully it will be clear. So let's say I have entries B, C. So B and C are symbols of somehow this way. So you look at all the occurrences of the letter C in the substitution of B. So the substitution matrix would just give a number count. But here, just put a sum of the monomials for each of the words, which are the prefixes of, so this denotes the prefix. So zeta of B is a word. There is all the occurrences of C, and then we look at the word immediately preceding it and look at the product of Z. So this is the definition. And actually, then we think about Z as being points on the torus when viewed multiplicatively. So then later we actually want Z to be written as 2e to the minus 2 pi I psi G, so that these are points on the torus written additively. So let me give an example. Hopefully. Okay, so let me consider that example. So there was 0 going to 0, 0, 1, 1 goes to 1, 1, 0, 1. So first of all, somehow it is more convenient to look at the now going along the row. So it corresponds more to the transpose substitution matrix. So so first we look at the appearances of 0 in the substitution of 0, and they are in the first place and the second place. So here we put 1 plus z0, and then there is a single 1 and preceded by twice 0, so we have z0 squared, and then substitution of 1, there is a single 0, so we put here z1 squared, and then there are 3 1s, so we put here 1, so for the empty prefix corresponds to 1, and then 1 plus z1 plus z0 z1 squared. Okay, so this way you can define this matrix. So there are many nice properties of this matrix. In particular, we can recover, given the matrix, we can recover the substitution. So remember, the substitution matrix forgets about the order. This keeps track of the order. And one, of course, immediate property is that this matrix, if we take, well, 0, but 0 if it's everything is written additively. So this corresponds to all the zj's being equal to 1. So actually, this way you get back the transpose substitution matrix. But the most important for us is that there is a cocycle property, which can be easily verified directly, that for any two substitutions on the same alphabet, it doesn't have to be the same substitution. So we can compose the substitutions. And then, so again, now I want to write this points on the torus additively. This is this matrix corresponding to the second substitution at the point where you apply the transpose substitution matrix to the point xi times this matrix corresponding to the first substitution at xi. And so this way we can define the cocycle. So the so to make it okay, so in order to define the cocycle, let's assume that for simplicity that the matrix substitution matrix is not singular. Okay, so then we can consider the toral endomorphism, which takes a point, takes a vector multiplied by the transpose substitution matrix, which of course is an integer matrix, mod ZB. So have a toral endomorphism, which preserves the Haar measure. It preserves Haar measure. Okay, so I define the spectral theory for invertible systems, but you can also do it for non-invertible. And if determinant is equal to plus minus 1, then actually it is a toral automorphism. Right? And basically what we have is so we have this matrix product, which actually can be written directly as this complex matrix corresponding to the nth power of substitution, right, which follows from this cocycle formula. And this is actually a complex matrix cocycle, is a complex matrix cocycle over this toral endomorphism. And in this situation, you can talk about the Lyapunov exponent. So in particular, Furstenberg-Kesten theorem says that there is a top Lyapunov exponent, which and we can also talk about local upper Lyapunov exponent, 0.5. So define the Lyapunov exponent. Now we assume that the toral endomorphism is ergodic. So it's well known that if there are no eigenvalues of the substitution matrix on this unit roots of unity, so then this implies ergodicity. So then well-known results. So it follows from Kingman's theorem, but originally proved by Furstenberg and Kesten, that there exists a Lyapunov exponent defined as a limit. If you look at the growth, exponential growth rate of the norms of the matrix, and this limit exists almost everywhere. Exists almost everywhere on the torus. On the other hand, for any point on the torus, one can consider the upper local Lyapunov exponent, which is just lim sup of the same, lim sup of the same quantity. And let me just point out that, of course, if you take this point, the 0, where you get the substitution matrix, then we know very well what it is, because it's just a logarithm of the Perron-Frobenius eigenvalue. So if the limit exists, then we don't put plus. So at the point 0, when the torus is written additively, this is just log of the Perron-Frobenius eigenvalue. Okay, so yeah, I didn't really state any results. Now let me state the result from joint and fit from a few years ago. So we make the usual assumptions about substitution, that it's primitive, aperiodic, and assume that the matrix, substitution matrix, is irreducible over the rational, so that the characteristic polynomial is irreducible over rationals. So if it turns out that this top Lyapunov exponent is less than half of log theta, then you have the system has pure discrete, pure singular, has pure singular spectrum, pure singular spectrum. We don't know if this is a necessary condition, but this is something that can actually be verified. And just interesting remark is that there is always a non-strict inequality. It could be surprising that there is always less than or equal to 1/2. There are always kind of big gap with from the Lyapunov exponent at 0 and the average Lyapunov exponent is at least less than or equal to 1/2. If we are below 1/2, then we know that it is singular. Okay, I think I still have a couple minutes, maybe, because it started, or maybe 2 minutes. So I'm not writing anything, just saying. So because I mean, I started with the twisted sums, and it's not clear how this is related. So let me just say that it all goes via this local dimension estimates, but the point is that if we, that actually the way to see the connection is maybe as follows. So why the spectral cycle? What is the reason for this? So remember, we started talking about this twisted Birkhoff sums. If we look at twisted Birkhoff sums at the point x, which starts with a n substitution of a given symbol, this is the length of the n substituted symbol, and you look at the simplest possible function, test function, just the characteristic function of a cylinder corresponding to a symbol j. So all the sequences which have j at 0 position. And this gives us a matrix, Ig matrix. So it turns out to be nothing but this spectral matrix corresponding to the cycle at the point omega times 1, vector 1, corresponding to n. And it turns out that these are actually important words to consider, that because of the special renormalization property of substitution, if we can bound this sort of all these twisted Birgel sums, we can actually bound arbitrary twisted Birgel sum uniformly. And this really comes from the bounds on the Lyapunov exponent. And then that, via the lemma, which I mentioned earlier, gives local dimension estimates. And then this inequality actually yields that the corresponding measure will have dimension greater than 1, Lebesgue almost everywhere, which implies singularity. So this was just trying to give a flavor. Thank you very much.